Stand with me on a quiet beach tonight, where the sand still holds the warmth of the day and the air carries the salt-sweet scent of endless water. Listen to the gentle rhythm that has played here for millions of years, the soft whisper of waves advancing and retreating, in a pattern so precise you could set your watch by it. Watch how the water reaches higher up the sand than it did an hour ago, claiming shells and driftwood that lay safely dry in the afternoon sun. This isn't random. This isn't chaos. This is one of nature's most elegant performances, choreographed by a conductor so distant you might barely notice it hanging in the darkening sky above. The moon, pale and serene, watches over this nightly transformation with ancient patience. For 4.5 billion years, it has been pulling at our oceans, commanding them to rise and fall with an authority that seems almost magical. Every 6 hours and 12 minutes, the sea obeys this celestial summons, turning harbors into mudflats and mudflats back into harbors, as reliable as sunrise, as mysterious as dreams. Coastal dwellers have witnessed this miracle so often it becomes invisible, like breathing or the beating of our hearts. Yet if you truly pause to consider what's happening here, it defies everyday logic. How can something 250,000 miles away, farther than you could drive in 10 years of constant travel, reach across the void of space to lift trillions of tons of water as effortlessly as you might lift a cup of tea? The waves that kiss your feet tonight began their journey not in some distant storm or underwater earthquake, but in the gravitational embrace between two worlds dancing through space. Every tide is a love letter written in water, sent from the moon to Earth across an ocean of darkness that would take light itself over a second to cross. But how does this pale orb in the sky move entire oceans, shaping the rhythm of our planet? Long before humans understood gravity or mapped the movements of planets, they lived by the wisdom of the tides. In ancient Babylon, astronomers in tall ziggurats tracked the moon's phases alongside the rising and falling of rivers that connected to distant seas. They carved their observations into clay tablets that still survive today, evidence of humanity's first attempts to decode this cosmic puzzle. The Phoenicians, master sailors of the ancient Mediterranean, built their maritime empire on tidal knowledge passed down through generations of seafarers. They knew that certain phases of the moon brought higher tides that could lift their heavy cargo ships over harbor bars that would ground them at other times. Their trade routes, which connected civilizations from Spain to Lebanon, were planned around these lunar rhythms as much as around winds and weather. But perhaps no ancient people understood tides more intimately than the Polynesian navigators, who transformed the vast Pacific Ocean into their highway across paradise. These remarkable sailors could read the subtle signs of tidal currents in the patterns of waves against their outrigger canoes, feeling changes in water movement that told them they were approaching islands still below the horizon. They developed a sophisticated understanding of how tides behave differently around coral atolls versus volcanic islands, knowledge that allowed them to navigate thousands of miles of open ocean using only the stars, the swells, and the moon's influence on the in medieval Europe. Coastal monasteries organized their daily prayers around tidal schedules, understanding that the rhythm of worship could harmonize with the rhythm of the sea. Monks in places like Mont Saint-Michel in France watched their abbey become an island twice daily as tides surrounded their rocky sanctuary, turning their home into a fortress that could only be reached when the moon allowed safe passage across the sand. Native American tribes along both coasts developed rich traditions connecting lunar cycles to the best times for fishing, clamming, and gathering seaweed. The Tlingit people of Alaska could predict which beaches would offer the most abundant harvest of shellfish by observing not just the moon's phase, but its position in the sky and the season of the year. Their survival depended on reading these signs correctly, and their oral traditions preserved this knowledge in stories that taught children to see the moon as a partner in their relationship with the sea. Even inland civilizations felt the moon's oceanic influence. The ancient Egyptians noticed that the Nile's floods, which brought life to their desert kingdom, followed patterns that seemed connected to both solar seasons and lunar months. They developed calendars that tracked both cycles, understanding intuitively that their river, which flowed from distant mountains to the Mediterranean, carried within its rhythm some echo of the great tides that moved the world's waters. These early observers developed elaborate mythologies to explain what they witnessed. The Greeks imagined Poseidon rising from underwater palaces to command the seas. Norse culture spoke of the cosmic wolf Fenrir, whose breathing caused the tides. Celtic legends told of sea gods who slept and woke in cycles that matched the moon's journey across the sky. For centuries, these patterns were tracked, but their cause remained hidden, until science turned its gaze skyward. The answer, when it finally came, was both simpler and more profound than any myth. In 1687, a man named Isaac Newton, sitting in Cambridge beneath apple trees that have become legendary, published a mathematical description of a force that governs not just falling fruit, but the motion of planets, the behavior of comets, and yes, the rise and fall of Earth's oceans. Gravity, Newton realized, wasn't just what kept our feet on the ground. It was the invisible hand that reached across space itself, connecting every piece of matter in the universe to every other piece with a force that grew stronger with mass and weaker with distance. The same force that pulled an apple toward Earth also pulled Earth toward the apple, though the effect was too small to measure. And the same force connected Earth to the moon in a gravitational embrace that had been shaping our world since both were young. Picture the Earth-Moon system as a cosmic dance partner, with both bodies constantly falling toward each other, but never quite meeting because they're also moving sideways fast enough to keep missing. It's like a perpetual, almost collision that creates a delicate balance. The moon pulling on Earth, Earth pulling on the moon, both locked in an orbital waltz that will continue for billions of years. But here's where the story becomes beautifully complex. The moon doesn't pull on Earth as a solid, uniform ball. Our planet is largely covered by water, and water, unlike rock, can flow and reshape itself in response to gravitational forces. As the moon passes overhead, its gravity pulls more strongly on the water directly beneath it than on the solid Earth below, creating a bulge of elevated ocean that follows the moon around our planet like a faithful companion. But wait, there's more magic to uncover. On the opposite side of Earth, another bulge forms, and this one seems to defy logic at first. How can the moon create high tide on the far side of the planet, where its pull should be weakest? The answer lies in understanding that the moon isn't just pulling on our oceans, it's pulling on the entire Earth. The solid planet gets tugged toward the moon more than the water on the far side, effectively leaving that distant water behind, creating a second bulge that mirrors the first. Imagine Earth as a tennis ball being gently squeezed between invisible fingers. The ball doesn't compress uniformly. It bulges out at the sides where the pressure is least. Our oceans behave similarly, creating two tidal bulges on opposite sides of the planet that rotate with Earth as our world spins beneath them. This means that as you stand on any coastline, you're actually rotating past these bulges of elevated water. When your part of the coast spins into one of these bulges, you experience high tide. When you rotate into the space between bulges, the water level drops to low tide. Because Earth spins once every 24 hours, but the moon takes about 25 hours to return to the same position overhead, because it's also orbiting Earth. The timing of tides shifts slightly each day, arriving about 50 minutes later than the day before. But if gravity is so simple, why do tides behave with such beautiful complexity? The moon may be the primary conductor of Earth's tidal symphony, but it doesn't perform alone. Our sun, despite being 400 times farther away, is so massive that its gravitational influence also reaches across space to tug at our oceans. Most of the time, solar tides work independently of lunar tides, sometimes reinforcing them, sometimes opposing them, creating a complex rhythm that would challenge even the most skilled composer. Twice each month, during the new moon and full moon phases, Earth, Moon, and Sun align in space like dancers finding their formation. During these celestial arrangements, the gravitational pulls of both Moon and Sun combine their effects, creating what we call spring tides, not because they happen in springtime, but because they cause the water to spring higher up the shore. These are the most dramatic tides our planet experiences, when high waters reach their peak and low waters fall to their minimum, creating tidal ranges that can be twice as extreme as ordinary tides. Picture standing on the shore during a spring tide at sunset. The moon and sun hang in the sky like two celestial partners, their combined gravitational symphony pulling the ocean into performances of extraordinary power. Waves that normally reach only to your ankles might surge up to your knees. Tide pools that usually lie safely above the waterline disappear beneath advancing seas. Harbor masters must prepare for waters that will rise higher and fall lower than their charts typically predict. But the cosmic choreography doesn't end there. When the moon reaches its first and third quarters, appearing as a half circle in our sky, it forms a right angle with the sun as seen from Earth. During these times, solar and lunar tides work against each other in a gravitational tug-of-war that creates neap tides, gentle, modest tides that barely whisper their presence on the shore. The word neap comes from an Old English term meaning without power, perfectly describing these subdued performances when the ocean seems almost to rest, gathering strength for the next spring tide cycle. The sun's influence creates other subtle patterns as well. Earth's elliptical orbit means we're sometimes closer to our star and sometimes farther away. When Earth reaches perihelion, its closest approach to the sun in early January, solar tides are slightly stronger, adding an annual rhythm to the monthly cycles of lunar influence. Similarly, the moon's own elliptical orbit brings it closer to Earth some months and farther away others. When the moon reaches perigee, its closest approach to our planet, lunar tides increase by up to 40%, creating what some call supermoon tides. These celestial mechanics create patterns within patterns, cycles within cycles, like a cosmic music box playing melodies of incredible complexity. Coastal communities learn to read these rhythms with the same attention that farmers once paid to seasonal weather. In the Bay of Fundy, where geography amplifies tidal effects, spring tides can create water level changes of more than 50 feet, enough to completely transform the landscape twice daily, turning fishing boats into playground equipment sitting on exposed mudflats, then floating them again 6 hours later. And yet, the ocean story is more than just a dance of gravity. It's a living system responding to the moon's rhythm that if you listen carefully to the sea, you'll hear something more profound than waves breaking on sand. You'll hear the ocean breathing, a slow, deep rhythm that inhales and exhales with each tidal cycle, drawing life-giving nutrients from the depths and spreading them across the shallows where sunlight can transform them into the foundation of marine ecosystems. Tides are the great circulatory system of our planet's waters, like the heartbeat that moves blood through a living body. As water rises and falls, it carries with it microscopic organisms, dissolved nutrients, and oxygen that sustains everything from the tiniest phytoplankton to the largest whales. In estuaries where rivers meet the sea, tidal mixing creates some of the most productive waters on Earth. Nurseries where countless species begin their lives in the rich soup of fresh and salt water stirred together by lunar forces. Consider the salt marshes that fringe temperate coastlines around the world. These seemingly simple grasslands are actually sophisticated ecosystems precisely calibrated to tidal rhythms. Twice daily, the rising tide brings marine nutrients inland, feeding specialized plants that can tolerate both salt water and fresh water. As the tide recedes, it carries away waste products and brings oxygen to roots that would otherwise suffocate in waterlogged soil. The plants, in turn, provide nursery habitat for juvenile fish, feeding grounds for migrating birds, and natural protection against coastal erosion that becomes increasingly important as climate change brings stronger storms and sea level rise to many shores. The timing of tidal cycles has shaped the evolution of countless species in ways both obvious and subtle. Fiddler crabs have internal clocks synchronized to tidal rhythms, emerging from their burrows to feed only when the tide is right. Grunion fish in California time their spawning to the highest spring tides, ensuring their eggs will be safely buried in sand that won't be disturbed by waves until the next spring tide cycle gives their offspring the best chance of reaching the sea in the deeper ocean. Tidal forces create underwater rivers of astonishing power. Tidal currents flowing around underwater mountains and through narrow straits can reach speeds that rival surface rivers, carrying nutrients up from abyssal depths to feed surface waters thousands of miles away. These deep tidal movements help drive ocean currents that distribute heat around the planet, making some regions warmer and others cooler than they would be in a world without tides. The Amazon River, though it flows through the heart of South America, feels the moon's influence more than 1,000 miles from the ocean. During strong spring tides, a tidal bore called the Pororoca travels upstream like a liquid earthquake, creating waves that surfers can ride for miles through rainforest channels. This twice-monthly invasion of salt water brings marine nutrients deep into the continental interior, feeding floodplain forests that help regulate Earth's climate by storing vast amounts of carbon. But tides do more than move nutrients. They also shape the very architecture of life along our coasts. Intertidal zones, those strips of shore that spend half their time underwater and half exposed to air, are among the most challenging environments on Earth. Yet they teem with creatures that have evolved remarkable adaptations to this twice-daily transformation. Barnacles seal themselves into waterproof chambers during low tide, then extend feathery feeding appendages when the water returns. Sea anemones retract into jelly-like blobs when exposed to air, then bloom into flower-like predators when submerged. These ecosystems serve as crucial buffers against the effects of climate change and rising sea levels. Healthy tidal wetlands can absorb storm surge that would otherwise devastate coastal communities. They sequester carbon more efficiently than most terrestrial forests, helping to moderate the greenhouse gases that drive global warming. As sea levels rise, these natural systems can migrate inland if we preserve the space for them to do so, providing ongoing protection for human settlements while maintaining habitat for countless species that depend on the rhythm between land and sea. But tides are not only about survival. They also write the story of human history. Walk through the streets of London at dawn, and you're following pathways carved by tidal wisdom. For 2,000 years, the Thames has been both highway and heartbeat of one of the world's great cities. And every building, every bridge, every wharf tells the story of human adaptation to lunar rhythms that predate civilization itself. Roman merchants building the first London Bridge understood that the Thames was two different rivers, one flowing seaward at low tide, another surging inland when the tide turned. They designed their harbor to work with these changes rather than against them, creating loading docks that could handle ships whether the water stood 20 feet high or 20 feet low. Medieval guilds timed their work to tidal schedules, knowing that certain crafts could only be practiced when the river was at the right height to power their mills or float their barges. The Great Age of Exploration was fundamentally shaped by tidal knowledge. Christopher Columbus delayed his departure from Spain until the tides were right for clearing the harbor bars. Magellan's navigators carried tide tables as precious as their charts of stars. Captain Cook's Pacific voyages succeeded partly because he understood how to read tidal patterns around coral reefs, knowledge that meant the difference between discovery and shipwreck on countless unmarked shores. Venice rose from tidal lagoons as one of history's most improbable cities, built on the understanding that the twice-daily rhythm of the Adriatic could be transformed from obstacle into advantage. Venetian merchants learned to time their arrivals and departures to catch favorable tides that would carry their heavy cargo ships over shallow passages. The city's famous canals weren't just roads. They were tidal rivers whose water levels changed throughout the day, requiring bridges and buildings designed to function whether the water was high or low. But perhaps nowhere has tidal power shaped human destiny more dramatically than in the Bay of Fundy, where the highest tides on Earth create a landscape that transforms completely twice each day. Mi'kmaq peoples lived here for thousands of years, developing sophisticated knowledge of how to harvest the bay's incredible abundance during the brief windows when receding tides exposed vast mudflats thick with clams, mussels, and marine worms. They built fish weirs, elaborate trap systems that captured salmon and other fish as tides carried them into shallow areas, then stranded them as waters receded. European settlers arriving in the 1600s were amazed by tides that could reach 50 feet in height, creating opportunities for mills powered by tidal flow. They built dikes to reclaim salt marshes for agriculture, but learned they had to work with tidal timing. Construction could only happen during the narrow windows of low spring tides when the water fell far enough to expose the work area. During World War II, The D-Day invasion of Normandy succeeded partly because Allied planners understood tidal conditions along the French coast. They needed low tide to expose German obstacles hidden beneath the water, but not so low that landing craft would be stranded on beaches. The invasion was timed to catch the rising tide that would lift damaged boats off the sand and carry reinforcements inland through shallow channels. The moon, in its way, helped liberate Europe. Even today, major ports around the world organize their operations around tidal schedules. Container ships leaving New York Harbor wait for high tide to clear the Verrazano Narrows. Oil tankers entering the port of Houston follow tidal windows that allow them to navigate the ship channel safely. The global economy still moves to rhythms established long before humans walked the earth. Even today, in our age of satellites and engines, tides continue to shape our future in surprising ways. From space, Earth's tides are invisible to the naked eye, but satellites equipped with precision instruments can measure the subtle bulging and flattening of our planet's shape as it responds to lunar gravity. These orbital observers have revealed that tides affect not just our oceans, but our solid Earth as well. The ground beneath your feet actually rises and falls by several inches twice daily, following the same gravitational rhythm that moves the seas. Modern oceanographers use supercomputers to model tidal behavior with extraordinary precision, accounting for underwater mountains, the shape of coastlines, the depth of ocean basins, and even the rotation of the Earth itself. These models can predict tidal heights years in advance, allowing coastal communities to plan for everything from construction projects to holiday beach trips with scientific accuracy that would have amazed ancient observers. But perhaps the most exciting frontier in tidal science involves harnessing this ancient energy for modern needs. As the world seeks alternatives to fossil fuels and grapples with the challenges of climate change, engineers are developing technologies that can capture the moon's gravitational power and transform it into electricity that could light cities and power industries without producing greenhouse gases. Tidal energy facilities operate like underwater wind farms, using the predictable flow of tidal currents to turn massive turbines anchored to the seafloor. Unlike solar and wind power, which depend on weather conditions that can change unpredictably, tidal energy offers the reliability of celestial mechanics. The moon will continue to raise and lower Earth's waters with clockwork precision for billions of years to come. The first commercial tidal power plant was built in France in the 1960s at La Rance, where engineers constructed a dam across a tidal estuary that generates electricity as water flows in and out with each tide cycle. More recent projects have developed less intrusive technologies, underwater turbines that generate power from tidal currents without blocking fish migration or altering coastal ecosystems. Scotland has become a world leader in tidal energy development, with arrays of underwater turbines installed in the Pentland Firth, where strong currents created by complex tidal interactions around the northern islands generate predictable power that could eventually supply significant portions of the nation's electricity needs. Similar projects are under development in Canada's Bay of Fundy, where the world's most extreme tides create energy potential equivalent to several nuclear power plants. Advanced materials science is making these projects more practical and cost-effective. New turbine designs resist corrosion from salt water and can operate efficiently in the harsh underwater environment where tides create their strongest currents. Underwater cables designed for offshore wind farms are being adapted to carry tidal-generated electricity to shore, creating infrastructure that could eventually connect tidal energy facilities across entire ocean basins. Climate change research has revealed new urgency around understanding tidal systems. As sea levels rise due to global warming, tidal patterns are shifting in subtle but measurable ways. Coastal communities that have planned their infrastructure around centuries of tidal observation may need to adapt to new patterns as ocean temperatures change. The density of seawater and melting ice sheets alter the distribution of mass around our planet. Scientists are also discovering that tides play crucial roles in regulating Earth's climate systems in ways that weren't fully understood until recently. Tidal mixing helps distribute heat between tropical and polar regions, affects the absorption of carbon dioxide by ocean waters, and influences weather patterns that extend far inland from coastal areas. Yet, despite all we've learned, the tides still whisper secrets we have not fully uncovered. Return with me now to that quiet beach where we began, where the sand still holds the memory of today's heat, and the night air carries stories of salt and time. The waves that reach toward your feet have traveled across oceans, perhaps touching shores in distant lands before the moon's gravity guided them to this moment. This place where you stand, witnessing one of the universe's most elegant demonstrations of connection across space and time, each wave carries within it the history of Earth's 4.5 billion year relationship with its lunar companion. The same gravitational dance that moves tonight's tide also stirred the primordial seas where life first learned to harness chemistry and sunlight. The rhythm you hear in the surf has been Earth's heartbeat through the rise and fall of countless species, through ice ages and warming periods, through the long journey that led from single-celled organisms to the complex ecosystems that surround you now. The moon hanging above you tonight is the same moon that guided ancient navigators across unmarked seas, that inspired the first astronomers to imagine forces reaching across empty space, that continues to power the circulation systems that bring nutrients to marine life and moderate our planet's climate. Every tide pool reflects its light. Every grain of sand has been touched by its influence. Every creature that depends on the rhythm between land and sea carries within its biology the memory of lunar cycles. But the story continues beyond Earth's shores. As humans venture back to the moon and eventually to other worlds, we carry with us the knowledge earned from millennia of observation, from ancient tide watchers to modern satellite observers. We understand now that gravitational relationships shape not just our own world, but every planet, every moon, every system of worlds throughout the universe. The tidal forces that created Earth's vast oceans also heat the interior of Jupiter's moon Europa, potentially maintaining liquid water beneath miles of ice where life might even now be stirring. The same physics that Newton first glimpsed in apple orchards helps us predict the behavior of binary star systems millions of light years away, where gravitational tides stretch matter into streams of plasma that spiral into black holes. The moon has been our teacher, showing us through accessible, beautiful daily demonstrations how matter and energy connect across the cosmos. Standing here tonight, you are part of this continuing story. The calcium in your bones was forged in ancient supernovas. The water in your body has flowed through countless tidal cycles. And the oxygen you breathe was created by marine organisms whose lives have been shaped by lunar rhythms for hundreds of millions of years. You are not separate from the cosmic dance that moves the tides. You are part of it, built from its elements, sustained by its patterns, connected to its past and future. Listen to the waves, and hear in their rhythm the heartbeat of a living planet still young in cosmic terms, still learning, still changing, still responding to the gentle pull of its companion as both worlds continue their journey through space and time. The tides remind us that we are part of a larger rhythm, a cosmic song still unfolding with every wave, every breath, every moment of wonder as we recognize our place in the vast, interconnected symphony of existence. The moon will rise and set, the tides will ebb and flow, and the ancient conversation between Earth and its companion will continue long after tonight's waves have whispered their secrets to shores you will never see. But for this moment, in this place, you are witness to the eternal bond that connects worlds across the darkness, bringing the universe itself to dance at your feet in the form of water rising and falling with celestial grace.